explain the different types of planets that we observe on the basis of a hypothesis that says that the solar system contracted from a cloud of gas and dust. Well, in order to do that, we need to bring in other scientific knowledge, specifically the particle theory of matter, or the kinetic molecular theory that was developed by John Dalton around 1800. You learned about this in grade 9. I hope that you're familiar with it. The important point for us here is that Dalton figured out that the particles that make up all matter have speeds that are directly related to the temperature of that matter. So in other words, the higher the temperature of the matter, the faster the particles are moving. This is important because remember that we discovered that all the planets that are close to the sun are made mostly of rock with metallic cores. All the planets far from the sun are gas giants, and then very far from the sun we have the tiny icy trans-Neptunian objects. How can we explain these differences? Well, the obvious other difference in these regions of space is temperature. Very close to the sun, in the realm of Mercury, the temperature in the environment is about 1300 degrees Celsius. But as you move out further from the sun, the temperature goes down. And somewhere between Mars and Jupiter, you hit a point where you're far enough from the sun so that the temperature is 0 degrees Celsius. Astronomers call this the frost line because beyond that frost line, any water that's present will freeze into the form of ices. So for the gas giants, the temperatures are well below the freezing point of water and below the freezing point of many other materials. When you get out to the realm of the TNOs, the temperatures are down around minus 220 degrees Celsius. And this, as kinetic molecular theory tells us, can explain the differences in composition. In the inner solar system, where the temperatures are relatively high, the gas particles, as they're being blown away by the solar wind from the sun, kinetic molecular theory tells us that these particles will be moving quite quickly. In fact, they'll be moving too quickly for the gravity of the growing planets to actually hold them. If you know anything, if you've ever played football, if you're trying to tackle somebody and they're moving they're already running really fast, it's going to be really hard to hold them. You put your arms around them and their momentum just carries them right through your grip. Well, the same thing happened to the gas particles of these inner planets. As they were moving so quickly due to their high temperature, they just shot right past the growing planets, and therefore the planets couldn't accumulate very much gas, and they ended up being composed only of the solid material, the dust. And remember, that made up only 1% of the solar nebula. So if you're going to build a planet out of only 1% of the material, that planet's going to be pretty small, and it's going to end up with only a very thin layer of gas that can be held. We'll see, in fact, that we don't think this gas is originally from the solar nebula. It was added later, but even so, with our small gravity, the Earth can only hold a thin atmosphere. On the other hand, in the outer solar system, the sun is much further away and the temperatures are much lower, so the gas particles are moving much more slowly. In fact, they're moving slow enough so that the gravity of the planets can actually trap the particles and hold them. So here come our slow-moving gas particles that get pulled in by the gravity of the gas giants. Now what's going to happen here is we're going to set up another positive feedback loop, because having added more gas, more matter to this object, we've actually increased its gravity. By increasing its gravity, it can pull in more gas, which is going to give it more mass, which means it will have more gravity, which means it can pull in more mass, and it will keep accumulating any gas that's anywhere nearby. And it'll keep accumulating gas until all the gas in the area has been pulled in. And hence, you end up with a gas giant with its solid core surrounded by the slow-moving gas particles to form this really, really thick atmosphere. And thus, we form the gas giants. We think they all have those solid little cores, which, because they were far from the sun and were at low temperatures, could accumulate the slow-moving gases. If the Earth had been further out from the sun, then it too would have been able to accumulate these gases and formed into a gas giant. Out beyond Neptune, the sun is very far away, the temperatures are very low, the gas particles are moving really, really, really slowly. In fact, so slowly that rather than simply being caught by the growing planets, which are very small here anyway because there's not much material, because Jupiter and the other gas giants have gobbled it all up. But any gases there will actually slow down enough that they will freeze into little tiny chunks of ice. And then those little tiny chunks of ice can join together, can accrete with any little bits of dust and rock that are out there, and can form the icy, dirty snowballs of Pluto and the other trans-Neptunian objects.